So I'm going to talk about the uses of wood in rivers real quickly. Some design considerations also. Sounds like a elephant seal. Yeah. Mating season.
Make sure you put that in your review. I'd like to see
Yeah. Okay. So why do we want to put wood in streams or use wood? Well, wood's a natural component of forested systems. Wood provides, well, and just to step back a little bit, so the density of wood obviously varies from place to place. You might find wood in prairie streams too, but at a much lower density. So in old growth forests, like out in the Olympic Peninsula, for instance, you might have wood densities of 50 or more pieces per 100 feet. And then in second growth forest in the Midwest, for instance, you might have 5 to 10 pieces per 100 feet. So a tremendous amount of variability there. We've removed much of that wood, and so I talked a little bit last night about jump-starting some of these processes. So we've also eliminated the recruitment of wood, which can take quite some time, and so we can kind of jump-start that process at the same time as restoring our riparian zones. What can you do with wood? Well, you can do a lot. You can stabilize banks in strategic places like in this project here, creating local scour as well and fish habitat. Oftentimes the benefits are combined. You can create scour pools. You can use wood as grade control and as channel boundaries, or at least temporary channel boundaries, especially in smaller projects. You can use wood on a larger scale as a roughness element, and a lot of this wood might not even be in the channel, and the fish might never see it. But in the project on the right, so the restored channel is up above the photo, we can't see it, but the old channel was filled in, the ditch, and in order to reduce the risk of avulsion or the stream recapturing that channel, you can load up that old channel with wood. And a tremendous amount of roughness kind of trains the flood to go where you want it to go, essentially. In the photo on the left, there's some side channel work been done there, and so some of the wood is, the vertical stuff is there to simulate older growth forest roughness and collect other wood, and then also to protect the entrance and exits of those side channels. You can use wood again, log jams as channel stability measures, but again also serve to provide fish habitat as well. You can integrate wood into harder treatments or integrated treatments like riprap, for instance, if you're trying to protect some infrastructure, like a house in this case. So it's important to understand what the risks are before we talk about design considerations. So primarily the problem is if your wood comes loose and floats downstream, and that can cause issues. So it can ruin your project, which is a bummer, and your habitat and goals can be lost. Maybe you were using the wood to manipulate the geomorphology or the sediment of that stream a little bit, and those goals can be lost as well. You can clog up culverts and bridges, and that can cause flooding, and you can destroy those structures as well, and you don't want to send a log through somebody's basement window. So I talked about this last night, the umbrella of due diligence, and so on the far right here, you kind of have a slightly elevated level of you need to address the moment force considerations, which we'll talk about a little bit, and then also fitting the project to the geomorphic setting, as always, but with regard to wood in this case. So what are the forces at work? So drag force and buoyant force are the primary forces that we're concerned about. And drag force is essentially dependent on area and velocity. So you can start out with a wood complex that has a certain amount of area to it, but you have to watch that area change over time because wood collects other wood. And so your drag force in the beginning of the project might be different than it is a couple of years later. And then, of course, it's higher around bends and steep areas where you might have velocities that are greater. Boring math. Buoyant forces. Buoyant force is usually the big one in the Midwest, especially on lower gradient systems. So buoyant forces, if you have a beach ball and you try and sink it in a pool, it takes a lot of weight. The amount of weight that it takes to get that underwater is equal to the amount of weight that you would have if that bowling ball was, or that beach ball was filled with water. So it's essentially buoyant force is equal to the weight of the displaced volume in water. So if that makes sense. So just to run through a quick example, so if we're going to calculate the ballast needed to keep a log around, let's say a 35-foot log that's 1 foot in diameter, the buoyant force of that wood works out to be about 1,200 pounds, and that's that upward red arrow. The downward force components then would be the weight of the wood itself, which is, in this case, 1,700 pounds. And the weight of the soil that's on top of it, we're assuming that we're burying 10 feet of that log. And so, is that enough? The total of those two blue ones is then, of course, 4,500 pounds, which is well in excess of, if you were to use a factor of safety of 2, for instance, you're probably okay. Assuming that, of course, your countermeasure stays in place. And that's a big assumption. So compare that to the same amount of drag, or the drag force for that same log. In this case, only 310 pounds with some assumptions about velocity. So a lot of times the buoyant force is going to be well in excess of the drag forces at work. Other considerations you have to think about, just because you did the calculation doesn't mean that everything's going to be fine. Wood can vibrate, especially during flood flows. You've seen this if you're canoeing down a river. You see sticks kind of vibrating in the flow. And logs can do this too. They start to pump out soils when they do that. And you get friction loss there. And wood can slide out. It can torque and start to dismantle your project. And that's why I have the Jenga reference up there. You pull out the wrong pieces, and you're going to have problems. Things change over time, too. Remember, the area changes as wood collects debris. Wood dries out if you're in a wet, dry environment. Your wood can rot, for one, and disappear, which is a problem. And it also gets drier over time, and as it does that, then the buoyant force essentially increases, because the downward force component becomes less. So what can you do to keep it in place? You can do nothing. In this project here, it's just wood that's dropped by a helicopter, and you know, the idea is that you're out in places where risk is low, and but you want the wood to move. In this case, you just want the stream to do it. And so you're introducing the material into the system, and then what becomes of it is sort of up to nature. And so sometimes that's okay. Or if you're in a spring creek or something like that, maybe you don't need to ballast wood because you're not getting a flood ever. Or the risk of a flood is low, or the risk of infrastructure damage or something like that is really low as well. You can use soil, of course. Things to consider there are, you know, the density of the soil, the mass of the weight on top of your wood. You know, you still need to do all the buoyancy and drag stuff, but here, especially when you don't have a lot of protruding wood, drag force isn't going to be that big of a deal. Sometimes if you remember now, the amount of ballast on top of your wood can decrease if that ballast disappears. So if you have a big flood and all your soil goes away or starts to winnow out, now your ballast is reduced. So you may need to combine that with some bioengineering or something to keep that soil in place. You can use driven piles or dug-in piles. This primarily uses friction, but they can be really strong. I mean, if you drive a pile in, a vibratory pile, you know, 20 feet down, you can get 20 or 30,000 pounds of ballast on something like that. And so, and they serve other purposes, like I had said before, you know, creating immediate big old wood roughness, and also collecting debris. And you can do things like cabling. In the left there, some people don't like cable. A lot of people don't like cable, and there's certainly debate about when and where to use cable. And sometimes you don't need to use anything. Sometimes you need to use it strategically. It can be buried. It can be way deep in the jam or in the structure that you're building. Threaded rod is something that is used out west on occasion on big structural projects. You can cut the stuff off right at the log. But again, you know, it's steel, you know. So anchors, you know, have a limited amount of they have a limited amount of performance. So you have to be kind of careful if you're using like duckbill anchors and things like that. They can't hold a lot of material, and they sometimes are hard to drive in, especially if you're in coarse soils. So they've been throwing around, and actually we've done a couple of jobs where we're using big rope or really strong rope. The trouble with rope is that it's easily cut by vandals, etc. I mean, it's not that you couldn't take a cable cutter out there, but most kayakers don't carry them with them. So in a lot of these, you're using the complexity of the jam itself as a countermeasure. And so the bigger the wood or the more complex the jam, the less it's likely to move. You can actually use rock, like in the right picture, you're embedding boulders into the matrix of the log jam in this case. They're not anchored by cable in that situation, much easier situation, or you can actually tie it to logs with cable. And you know, you could spend Bob and I were just at a workshop on wood that was a week long. I mean, so you can spend a lot of time obviously on these things, but just talking about where to fit it in the geomorphic setting is a whole couple days worth of discussion. So all I'll say about that is, you know, the important thing is to know where the wood is naturally going in the system, where it might go if you were to change things by adding a lot of wood, if that's your goal, and to really realize that, again, the mobility of wood is really dependent on the length of the wood in a lot of cases. And so if you're longer than bankful, your wood's much less likely to move. And if it does, it's going to get caught up on some planform geometry downstream. So if you have a bend or some floodplain roughness, that's usually where the stuff locks up. And wood behaves differently given the size of the river. So what kind of wood is good? Density does not correlate directly with rot resistance. So cedar, which is great, is actually less dense than cottonwood, which is terrible in terms of its longevity in the Midwest. If you're out west, cottonwood lasts a long time. But if you're in the Midwest, in an urban area, say, or an area that's wet dry, you might get 2 or 3 or maybe 5 years out of that cottonwood log, unless the log sprouts up, which I'll talk about in a sec. So lignin content, resin, tannic acid content, these all go into contributing to the longevity of wood in your system. And so the preferred species around here, cedar, you're never going to get it. But if for some reason you had a chance to use cedar and if somebody had some, that'd be great. You might think about selling it actually for lumber instead and then using that money to buy other wood. But white pine, a lot of the pines are good. Oak, elm has a really high density, can last a long time. Some of these that are on the bottom are normally not the best because they're soft and they disappear quickly, but if you can work them into a jam that's getting exposed to water, they'll actually sprout up and come to life. And now your wood starts to get a whole nother level of stability. And lastly, there's, especially out west, there's been a lot of to-do about recreational boating. and the risks of large wood to recreational boaters. And so kayakers get trapped up on log jams naturally and drown or get into trouble and need to be rescued. And there are also some attractive nuisance issues with children, playing on them. But I mean, the primary issue is boaters. And so what we're having to do on our western projects is build these bumpers sometimes that just train the kayakers away from the structure and keep them out of harm's way. And so when you're designing projects that are using wood around here too, you need to consider when people are going to be using the water, what elevation the water is at that time, and how that's going to interact with your wood structure. So you don't want to have things protruding out that are just going to tip people over, trap them, because you won't gain any support for what you're doing if you do that sort of thing. You can design a lot of wood that's really low profile, and so people just float right over it. They don't even know it's there. So there's a couple of white papers out there if you Google it, liability issues associated with large wood. You can read it for yourself. But what's that? Oh, those are super sacks. So they're just a temporary, not a dewatering mechanism, but you just use usually gravel or material that's on site if you're excavating, or if you're not, you have to bring in sand or something like that. But they're 4x4 usually. I think they make 5x5 bags too. And then you can just move them around with the excavator, build a little coffer dam, and separate your work area. You can use them for dewatering. You just have to drape them with Visqueen or some kind of material that actually separates the flow out completely. So, take-home message: treat each project individually. Properly assess your risk. Conduct the appropriate amount of due diligence in geomorphology and engineering, and then match the wood to the geomorphic setting, and then lastly, be safe. Wood is, it's inherently dangerous being around a construction site in the first place, and if you're tossing wood around, that gets even more dangerous. So wood can bounce, and if you are standing near a guy and he drops the wood out of the bucket, it can bounce and hit you. Or it can bounce and hit another piece of wood, and that piece of wood hits you. So I always tell the story about how I was standing about 60 feet away from the excavator one time, and he was dragging a root wad along the ground, and he hit a piece of wood, and that hit another one, and that hit another one, and it just flipped me right up, knocked me on my keister. So you just have to always be safe on the construction sites. So that's all I've got. Thank you very much, and I'll take some questions, I guess.
Questions?
Way in the back.
Yeah, way in the back. We got a microphone. Okay, the question is, I know you said that buoyancy forces were more important than drag, but I was curious if you found some good reference material to come up with the drag coefficient for large woody debris.
Yeah, so that's not always the case. Sometimes buoyant force is more than drag force, but there's some literature out there, and I can point you to an engineer or two from our outfit who are here if you want to talk about that in some more detail. But yeah, the answer is yes. So, yeah.
Hi, I was just wondering if you have any guidance for dealing with ice impacts?
Yep. So that's a big deal. That last picture I showed about the recreational paddling, that's on the Methow River in central Washington, and ice is a big deal there. If you build these beefy structures, they can handle a lot of punishment. If you're putting in individual pieces for habitat, things like that, those can be much more subject to loss. The same kind of things apply. The complexity of the jam, the mass of the work that's there, All those things go into being able to protect that structure from ice damage. And the logs can get beat up, but they generally seem to stick around. So it helps if you have the piles driven. It seems to add a lot more stability to if you're just doing like a loose jam or a log jam. If you're building things like tow wood or lower profile structures or habitat work, sometimes ice passes over the top of that. So there's a paper about, a couple papers about the impact of ice on bridge piers that I might point you to. If you're curious about that, there hasn't been a lot of work done on studying the effects of ice on log jams though. So it's a black box. Yeah.
Other questions? We got time for another couple? At least one?
Is there a big difference between the species selection and the invertebrate recruitment?
I don't know the answer to that question. Well, certainly certain macroinvertebrates use wood more than others, right? And so the good part about putting wood in a stream that maybe had it historically but doesn't now is that you give those organisms an opportunity to flourish, I guess. But yeah, I don't know. Don't know the answer to that one.
Last one.
If you're doing a hydraulic model of a reach, how do you consider the wood? Do you adjust the roughness or adjust the stream cross-section?
Yeah, obviously you're limited if you're doing a 1D model, for say, or even a 2D model. But yeah, I mean, adjusting roughness is pretty much all you can do, or you can add it in as a structure, like a bridge pier, for instance, if it's a really big jam. Yeah. I don't know if you have another answer to that, Bob, but
Typically what I do is I use the obstruction tool.
yeah.
I do that and then adjust according to roughness on both sides. All right. Thanks, Marty.
Yep, thank you.